Okay, hi everyone. This is a recorded run of my talk that I'm going to be giving at UseR 2024, which is going to happen in Salzburg in a week. And I'm doing this on video in case you can't make it, or if you want to attend another talk at the same time, that's fine. Just listen to this instead. So the talk is about how to interpret statistical results with marginal effects, which is a R package that I've been maintaining and developing over the last few years, and I'm really excited to present it. So who am I? I am a professor at the Université de Montréal in Canada. I've been publishing packages on CRAN for about 15 years, so it's been a while, and I plan to keep on doing it. I like it. It's fun. I've recently been named as an associate editor of the R Journal, so send us your papers. It's a nice journal. It's good. Send us your stuff. Okay, so that's me. Today, I'm going to discuss two main problems that I believe affect, well, certainly affect me and almost certainly you. I think most people who deal with data have to deal with these problems. The first one is that our outputs and really software outputs in general are pretty inconsistent when it comes to statistics. So here's just a simple example. So you have this predict command that is in R that everyone has used almost certainly if you're at this conference. So predict computes fitted values for your model. So you do predict mod, and then oftentimes you'll write comma se fit to get standard errors around your predictions, essentially. And what's interesting to note is that depending on the type of model that you fit to this function, you're going to get wildly different results. So if it's a GLM model, for example, you're typically going to get a list with two vectors and one scalar. So you'll get the fitted values, you'll get standard errors around those fitted values, and you'll get something called residual scale. Now, if you do something else, you estimate a ordinal logit model, for example, using the pol_r function. Then if you do the exact same command, you run the predict comma scfit true, you're going to get a matrix of estimates and no standard errors. So that's kind of weird, and it's annoying, and it's a problem that everyone has to deal with. When you use different modeling packages, oftentimes these will behave slightly differently. I mean, it's not so bad. R is great, and the packages are great, but there are inconsistencies, and it can really slow you down. So that's one problem. The second problem is more basic. It's just that stats is really hard. So take this example. So imagine you estimate a logit regression model. So that's just with the standard GLM function. So the dependent variable is bin because it's a binary variable. Then you're going to have two predictors, a numeric one that's just a continuous variable, maybe normally distributed or something like that. And then a categorical variable with three levels, A, B, and C. So you estimate this super simple, basic logit model. People see this in their, let's say, second stat class or something. So it's a very simple model, and you have the coefficients on the side, right? And so even though this model is pretty simple, I would argue that it's surprisingly hard to interpret. So first of all, people are just terrible at interpreting probabilities in general, right? So if you look at the literature in psychology and in behavioral economics, for example, there's really lots of evidence that people cannot do this properly. When the probabilities are very high, they tend to have a bias and not interpret it correctly. Same thing with very small probabilities. So it's just a really hard thing to interpret probabilities. And if probabilities are hard, these kinds of expressions there, the log odds ratio is much harder. And really, for most non-specialists, I would argue that's an expression like this, which corresponds to a logit coefficient, of course, is really much harder. So when you look at the individual estimates in this table, like this one there, well, it's really hard to say exactly. Well, it's maybe possible to give a specific definition of it, a very classical definition of it. It's possible, but to get a gut understanding of this thing is really much harder, I think. So what we do is in these stats classes or in practice, we develop a bunch of very specific model-specific tips and tricks. So we'll exponentiate these coefficients, for example, or do something like this. But what happens if you move beyond this simple logit model? You have a model with interactions, you have a model with splines, you go for a multinomial model maybe, or even some machine learning algorithm like XGBoost. So what do you do then? How do you interpret your model? Well, then you're going to have to rely on, yet again, some model-specific tips and tricks. And oftentimes, well, people just don't know what to do. So the question here is that stats is hard. What do we do after we fitted the model? How do we interpret those parameters? So the one solution that I'm going to recommend to people is to do post-hoc transformation. So this is a quote that I like from Philip David. He says that a parameter is just a resting stone on the road to prediction. And so parameter estimates by themselves, I would argue, are usually very difficult and sometimes basically impossible to interpret as is. And so in our practice as statisticians, as social scientists, as data scientists, we often need to transform parameter estimates to create quantities that stakeholders will understand and care about. Basically, nobody cares about the parameters of your models. And so you better make sure that those parameters are represented in a way that makes sense, that is intuitive, that yields understanding and actionable insight. So using these post-hoc transformation, that is, you take your model, you fit it, you get your estimates, and then you transform those estimates, then that can help you do better, I think. Okay, so how do you do those post-hoc transformations? Well, I'm proposing the marginal effects package, which I believe is easy, consistent, flexible. It supports over 100 different types of models. So whether you estimate a GLM, a GAM model, some Bayesian thing, or a mixed effects multi-level model, or even some machine learning models. So it's compatible with the tidy models and the MLR3 ecosystems. So regardless of the model type that you use, almost regardless, you'll be able to use a single workflow with a unique set of commands that do a lot of what you want to do. And so all of this is documented in a free online book that is already online at marginaleffects.com that I encourage you to visit. And it has 30 plus chapters with really detailed explanations and case studies. And it's I spent a lot of time on this, so please look it up. I think it's a good website. It has cute illustrations of animals and such. All right, so what does this package do? Well, it offers basically 3 different quantities or sets of quantities that you can compute. The first one is just straightforward predictions. So oftentimes we call those fitted values, but they can be made for different predictor values. So we're going to use the predictions, the average predictions, and the plot predictions functions for this. Then we can do counterfactual comparisons. Those counterfactual comparisons are basically just functions of 2 predictions. And you'll see that we can express a lot of different quantities of interest as these counterfactual predictions. So you can do contrast differences, like a risk difference. You can do risk ratios. You can do odds, lift. All these quantities can be expressed as functions of 2 predictions. And this is what I'm going to call a counterfactual comparison. And then finally, you can do slopes. So that's a partial derivative, essentially. In some literature, in some disciplines, we call this a marginal effect. And that's going to be estimable using the slopes function and family. So the key of this package, what's really great, is that you can then, once you've estimated these quantities, once you've transformed the parameters of your models, you can run hypothesis tests on all of the quantities, and you can compare different quantities very easily with the package. All right, so here's the demo. So first, we're going to start with this function called hypotheses, which I haven't spoken about yet, but which this function has a hypothesis argument that's going to be carried over through all the other functions. So let's start here. So imagine that we look at the same logit model we used earlier. So it has an intercept and some coefficients there. Now, imagine that I have a null hypothesis that I want to try to reject. That is the beta 3 is equal to beta 4. So this is a hypothesis test of coefficient equality. So what I do is I use hypotheses, plural. That's my model. And then I specify my hypothesis using this argument. And I say B3 equals B4. Okay, and so the output there is the null hypothesis that these 2 things are equal. and I see that the standard error is pretty small, and the z value is big, and the p value is pretty small, and so I can reject the null hypothesis that these two coefficients are equal. So this is a very, very simple test, but you could do much more complicated tests. So this was just a linear test, essentially. But you can do any, almost any function that is evaluable in R. So you can do like exponentials or logarithmic transformations and set those hypotheses. I'm just showing you that this is a really, really flexible argument. All right, so the killer feature here is that the hypothesis argument is available in all the functions of this package. So if you compute predictions, you're going to be able to run hypothesis tests on those predictions. Same thing for counterfactual comparisons or slopes. And so this is going to allow you to answer really important scientific questions. So for example, if you compute the predicted probability of survival for men and women, you're going to be able to run a formal statistical test to determine if the two predicted probabilities of survival are equal, if the men survive at the same rate as the women. Or if you're going to estimate two treatment effect sizes, for example, so one for the old and one for the young, maybe like a pill works better for young people or something, well, you're going to be able to run a formal statistical test to compare these things. So is the treatment effect 1 bigger than treatment effect 2, or A and B? All right, so that's the killer feature, I think. All right, so let's move now to predictions. So as I said before, predictions are essentially fitted values. So in base R, what you would do is first you'd construct this data frame with the predictor values that you care about. So for example, in this case, I want the predicted value for an individual who is A on the category variable, on the cat variable, and 0 on the numeric variable. And then I would feed this data frame to the predict function. So you do predict, model, then your data frame with the values that you want. And then using the type argument, you would specify what scale you want this on. So in GLM models, typically you have the response scale and the link scale. Here I'm picking the response scale, which is in the logit model just a probability. So this is base R syntax. It's been there for years. Nothing's changed here. There's nothing new there. What is new is this predictions function, and it has the exact same syntax plus some other arguments that we'll see later. But it's the same syntax, but it gives you much richer results. So first you get the estimate, the p-value, the confidence intervals. So this is great stuff already. Now, if you just run predictions without any argument at all, you'll get fitted values for all the rows of the original data set. So in this data set that I'm using here, there's about 200 rows. So you see there, like you see the top few rows, the bottom few rows, and then there's some omission. But these are the fitted values for all of them with confidence intervals. And this is just a basic data frame with pretty print. So you can extract you can extract columns in a very tidy, friendly workflow. All right, now this was predictions, but you get one prediction per row of the original data, but you could also do an average prediction. So let's say I want to make predictions for every row of the data set, but then I want to take their average. I just do average, that's a AVG prefix, and I do predictions, and then I get the estimate. And the estimate here is that the average predicted outcome for this data set is 0.5. So remember, this is a binary outcome in a logit model. So we're at 0.5. This is the average prediction in this model. Now, what is pretty cool is that we've added this by argument. So you can do average predictions by subgroup. So in this case, we had a predictor called cat. So we do average predictions mod by cat. And there you're going to see that the predicted probability that the outcome is 1 is really different in all these subgroups. So in subgroups, it's really low. So we have 19% chance that the outcome is 1 in the A group, but 84% chance that the outcome is 1 in the C group. So these are very different, and you get average predictions by subgroup with, again, all these confidence intervals and all the goodies. Now, let's go back to this hypothesis argument that I've told you a lot about already. So let's say we start with the same command as in the previous slide. There's nothing new here. We just make average predictions for each subgroup. Now imagine that I want to compare these subgroups. I want to say, is the first subgroup bigger than the second one? Or are average predictions in cat A, in category A, and category B equal. So that's the killer feature that I think is really important. So what I do here is I do the same syntax, but I add one argument, the hypothesis argument. And here I'm going to say, is the first row equal to the second row? So that's going to compare my 0.186 to 0.344. And what I see here is that, in fact, these things are different. They're about 0.16 apart. And that difference is statistically significant. So I can reject the idea or the hypothesis that these two predicted values or these two average predicted values are equal. So I do know that these groups are different in terms of the predicted outcome. Yay. All right, so just showing you very quickly, it is very easy to plot the predictions using the plot predictions function. So almost all of the arguments in that function are the same as in the other one. So there's a high level of consistency across interfaces there. So that's pretty nice. This is a standard ggplot object, so you can always customize it with all the themes that you want and the labels and such. All right, now let's move on to beyond predictions, beyond fitted values, to something that's closer to causal inference. So here I want to present counterfactual comparisons, and that's going to be contrast, risk differences, risk ratios, odds, lift, these things, okay? So imagine that you're interested in this kind of counterfactual question. How much does the predicted outcome, the predicted probability that bin equals 1, change when the predictor num increases by 1 unit? So I increase my treatment by 1 unit. How much does the outcome change in terms of predicted probability? So the expression there that you'll recognize probably as estimated risk difference, right? So this is what we get when we run the comparisons function and we specify that we care about the variables num. So when the variables argument is set to a value like this, it says, I'm interested essentially in the effect of increasing num. So what you see here is that there's the estimated effect of increasing num by 1 unit on the predicted probability of the outcome, okay, that the outcome is equal 1. Now, since this is a logit model, the actual effect of this num variable is going to change based on all the covariates in the model. So every single row of the data set has a different estimate of this risk difference. Now, since this is kind of unwieldy, we don't want one estimate per row of the data set. What we can do is do an average comparisons. So here we would get average difference in predicted probability that bin equals 1 associated with an increase in num. So the number here says that when I increase num by 1 unit, on average, it's going to reduce the probability that the outcome is 1 by 1 percentage point. Okay, so we compute the estimate for every single row of the data set, and then we take that average. Or alternatively, I could be interested in a bigger shift. So this is a change of 1 unit, but I could be interested in the effect of 5 units of none, or maybe it's a standard deviation of none, of num, or I want to move across the interquartile range or something like that, or from the minimum to the maximum. So all of these different treatment effect sizes or treatment sizes or treatment strengths, I guess, are very easy to specify in this. So in this case, what I'm showing here is the effect of a change of 5 units of num on the predicted probability that the outcome is equal to 1. The average comparisons function is super flexible. So far I've only shown you risk differences, but there's this argument called comparison, and there you can specify a lot of different comparisons. So you can do ratios. So how does the ratio of predicted probabilities change when num increases by 1 unit, right? Or you could do lift or odds, or you can even specify custom quantities. So that's a really powerful feature that I can talk to you about later if you come see me. It's kind of crazy. Like I stumbled on this feature by accident, and I'm really happy with it. Okay, so now what happens if you have different predictor types? So if you have binary, categorical, or numeric variables, the average comparisons function is going to be pretty smart about it. So num here is a numeric variable, so it's going to by default show you the effect of increasing by 1 unit. But if you have a categorical variable, it's going to show you all these comparisons. So it's going to go, what's the effect of moving from A to B, or from A to C? And you can do sequential, or you can do a reference, or you can do all these different things for categories. So that's all done automatically for you, or you can specify and customize it as you wish. And now we're back to the killer feature, right? The killer feature is the hypothesis tests on these things. So if you look at the first two rows of this, so the first one is the effect of moving from A to B on the predicted probability that the outcome is 1. The second row is the effect of moving not from A to B, but from A to C on the predicted probability that the outcome is 1. So these are two treatment effects, essentially, right? And we see that these two treatment effects are different. So the first one is 16 percentage points. The second one is 65 percentage points. So these things look different, but I want to know, are they different really statistically? Well, what I can do is use the hypothesis argument, which I've shown you already. So the question here is the average effect of B versus 1 equal to the average effect of C versus 1? And here we get an estimate. That's the difference in effect sizes, right? This is not an effect size. It's a difference in risk differences, right? So a difference in differences, essentially. And we see that this difference is indeed statistically significant. So we can rule out the idea that B has the same effect as C relative to A. Okay, very nice. All right, so just very quickly, we can do slopes with this. Slopes are partial derivatives, essentially, or marginal effects in some disciplines. So this is very quickly, this is a GAM model with some splines. These things I've always found are pretty hard to interpret, but here this makes it much easier, I think. We can evaluate the partial derivative of y, that's our dependent variable with respect to time, and evaluate that partial derivative at every point in the observed sample. So that's just this one command does all of that. And then we can plot predictions versus slopes. So I've shown you the plot predictions function already, but there's also a plot slopes function, which gives you, I don't have it. All right, my slides are broken. These two plots are beautiful next to each other. Believe me, I'll try to paste it maybe in post. All right, so that's it. So if you want more, there is more. So I've told you about this website, but this website has 30 different chapters of stuff. It covers all the quantities that I've shown you already. It tells you how to do these hypothesis tests, and it shows you a bunch of really more advanced topics. So how to do machine learning, how to do causal inference, robust standard errors and bootstrapping, conformal predictions, categorical outcomes. So if you do like a multinomial logit or something like this, equivalence tests, interaction survey experiments, IPW matching. This one is fun. That's some people call this MRP post-stratification, and then multiple imputation. So there are detailed case studies with code in both R and Python, actually. So look that up. And then just to finish, I want to plug two things that I've also been working on in parallel. So the first one is called TinyTable. And TinyTable is a dependency-free, very simple to use, super minimalist package that is, despite all the simplicity pitch, very flexible. So it takes data frames and it converts them to tables in HTML, LaTeX, Typist, Word, Markdown, and you can do all this fun stuff. And then if you're interested, I also maintain this package called Model Summary, which allows you to create both regression tables, regression plots, and data summaries. So if you want table 1s or table 2s, like descriptive statistics, it has super flexible and powerful capabilities for this, and it can save your tables in a bunch of format. So check those out. And if you have any questions about these or about marginal effects, I'm always super happy to chat. So send me an email or open a issue on GitHub or ping me on Twitter, and we'll engage. All right. Thank you.